Hi, and thanks for dropping by the eCave today. This episode was going to be a continuation on the 5161 expansion unit being attached to the 5150 PC behind me. However, I've had nothing but problems with the XTIDE Compact Flash LITE card I was going to put into the 5150 PC in order to copy the hard drive data, provided it's working though. So, if you're interested in all my troubles and how I went about diagnosing my issues and getting it working, well, by all means, step inside. Thanks for stopping by the eCave. As I mentioned, the XTIDE Compact Flash LITE card I was going to put into the 5150 PC has given me nothing but problems. I've ended up having to do a deep dive into how it works and operates in order to diagnose and work out what was wrong. So this episode is dedicated to that. I hope you stay and see all the troubles I went through and how I diagnosed it, because it may even help you. So let me begin with telling you about what happened first, and then it gets worse. So let's begin. The first thing I had to verify is that the IBM 5150 had the latest BIOS revisions, because without that it doesn't support hard drives. I took out the diskette drive controller card in order to get a better view of the BIOS chip and its path number. Thankfully, it contained the latest revision of the IBM BIOS for the 5150, which does indeed support hard drives. You can see the BIOS versions on the -0 degrees website. Now, with that out of the way, I began by validating the switch settings on the two diff switches which are on the card. The first diff switch sets the I/O address, and it was set to address 300. The second diff switch sets the ROM address, which was set to C800. The second switch also enables or disables the ROM on the card, and also enables or disables writing to the ROM on the card if you want to reprogram it, but more about that later. Once I verified the switches, I put in an 8-bit 16 megabyte compact flash card onto the XTIDE adapter and put it into the IBM 5150 PC. I had seen and read that the minimum DOS version to use with these cards was DOS version 3.30 or higher. Now, as it happens, I do have IBM PC DOS 3.30, and I therefore decided to use that. All the initial signs were quite promising. The IBM PC detected the ROM and displayed the XTIDE banner showing the I/O address 300 and ROM address C800, so all good. I then proceeded to use DOS 3.30 to get the compact flash card initialized using the DOS fdisk and format commands. I was going to use the select program that comes with DOS 3.30, but then remembered that although it does transfer all the DOS programs to the compact flash card, it puts them into the root directory, which isn't the best idea. It's a lot better to create a DOS directory to store all the DOS files and then put a path command into the autoexec bat file. That way you can access any DOS commands from anywhere, and your root directory is littered with DOS files. Now, after partitioning and formatting the card, I used sys to transfer the DOS boot files and then try to reboot. Upon reboot, it would simply hang on the XTIDE banner and nothing would happen. After several tries, I eventually replaced the 60 megabyte card with another one I had, which is 8 megabytes. I could also partition format and use sys to transfer the DOS boot files on that one, but it also hung on the XTIDE banner screen and didn't boot to DOS. I then went to the documentation for the XTIDE CF LITE card and noticed that the resistor R5 should not be installed on the card. But as you can see, my card had R5 installed. No wonder it never wanted to boot. I could now boot into DOS from the compact flash card, and with that I copied all the DOS files into a DOS directory and created a path statement in AutoExec path. So I was happy. What I did notice and also read on the VCF forums was the fact that the XTIDE BIOS version on this card is very old. The gurus at VCF strongly recommended an upgrade to a more recent version. With that in mind, I proceeded to remove the BIOS chip on the card. The BIOS chip was soldered in, as it's an erasable EEPROM which can be reprogrammed on the card. However, I didn't want to do that as it had already shown itself to work despite the old version. By having a socket, I could swap BIOS chips in and out at will. As I already have an EEPROM programmer, I had obtained a few 2764 EEPROMs, which means they can be erased using UV light and then reprogrammed. I therefore desoldered the original ROM from the PCB and installed a socket. I then proceeded to find a later version of the ROM code for this card and program that into the new 2764 EEPROM chip I have. First of all, we have to find a new BIOS for the XT Compact Flash Lite version. And if we go to the -0degrees.net website, here has a lot of good information about the XT Compact Flash Lite and has a more up-to-date BIOS, as I mentioned before. Now, this is the card I have, as you see here, and we can go and get the BIOS, which he has pre-configured for that particular card here, and I've already downloaded that. So we are going to start by putting in the EEPROM I have. The EEPROM, which is already in the compact flash card, is a 28C64, which is an electrically erasable ROM that I want to retain in order to swap back if required. So here I've got a TMS2764 EEPROM, which I'll program. I'll put it in here. Yep, it's ready. And then we have to find the EEPROM. Just type in 2764, and it's a TMS chip, which is a TI chip, and it's a DIP 28. So we select that. We can first do a blank check to make sure it is blank. So let's do that first. Yep, it's happy with that. And then we have to retrieve the bin file, And I've got bin files, and here's the file I've downloaded from -0 degrees. We open that, and you can see it's a release 625, so it's a 2023 version, so it's more recent. And all we have to do then is to program it and send it into the EEPROM. Once we've done that, we'll do another verify just to make sure that the firmware code is secure in there. Now that's done. Okay. We can do another verify. Let me see. Here's the verify. Yep, all good. With the new updated code in the EEPROM, I installed it into the XTIDE card and also decided to change the ROM address from C800 to D000. The main reason is the fact that the IBM PC uses C800 as an address for its hard drive, so there would be a conflict between the hard drive in the expansion unit and the combat flash card trying to use the same address. So, having changed the switches, I put the XTIDE card into the IBM PC and booted up. Sadly, the IBM PC didn't see the XTIDE ROM and simply booted from the diskette. I've tried everything. This is what happens just about all the time. The blinking cursor, because this is a 5150 that doesn't count up the memory. And then when I expect the XTIDE banner, it goes to DOS. I'll put the old BIOS, original BIOS back into the socket. Same thing. Occasionally it gives me the banner and boots up. But strangely, the ROM address settings is not the one I set on the switches. Yep, back to DOS. Very frustrating. I'm just showing you one take. I've tried this so many times, it's not funny. So, no matter what I did, it would never show the XTIDE banner, just boot to the MS-DOS diskette. Very frustrating. So, in order to diagnose this problem, I ended up doing a bit of a deep dive into the XTIDE card and how it works. So let me share that with you first, but first, obviously, you need some background. This is the IBM PC memory map. Back in 1981, the IBM engineers designing the 5150 PC chose the Intel 88 CPU, which could address up to 1 megabyte of memory. The basic version of the IBM PC only had 16 kilobytes of memory, so expanding it to 640K would have cost a fortune. In fact, according to ChatGPT, it would have cost over US $5,000 to expand it to 640K. Anyway, the IBM designers had to include input-output capabilities, so they added a cassette port, keyboard port, and an audio speaker to the motherboard as standard, and then 5 expansion slots for future and current input-output devices. 2 of those slots had to be used, one for the display adapter and the other for the diskette drive controller cards. In order to make all of these I/O devices functional, they also wrote what they called a BIOS. BIOS stands for Basic Input-Output System. It contains the program routines which the 8088 CPU uses to interact with all the input-output devices. The code inside the BIOS is called firmware as opposed to software due to the fact that it's inside a read-only memory chip. These firmware routines were the first ones executed by the 8088 until it loads the operating system. The operating system will also make calls to these firmware routines when interacting with input-output devices, IBM included in the original BIOS. In addition, the IBM engineers also included firmware routines for other expansion cards that were launched at the same time by IBM. Expansion cards like the parallel printer port, the serial interface card, and the monochrome and color graphics display adapters, and so on. That meant the 8088 CPU had to share this 1 MB memory space between the firmware routines within the BIOS, as well as using the memory as working memory. IBM chose to set the limit to working memory to 640K and use the memory space above that for display memory and the BIOS routines. They also set aside memory space for BIOS routines with firmware for some future I/O devices they hadn't even thought of yet. So when we look at the memory map of the IBM PC, we can see how it's been mapped out. At the top is the original IBM BIOS, which resides in the motherboard. Next below that is the cassette basic ROM, which is executed if the IBM PC can't boot from a diskette. The area above the 640K memory address is used by the display adapters. This is where the static RAM ICs are mapped into, which are located on the display adapter boards. All the data from this SRAM area is written to the display by the display adapters. Note that IBM included the BIOS firmware routines for the monochrome display adapter and the color graphics adapter in the original BIOS. That is why those adapters don't have any onboard ROM chips. Above the SRAM display area, IBM reserved ROM address space for future display adapters. This is where, for instance, the ROM BIOS chip on VGA cards maps to in the address space. Then, above that area starting from address C800, IBM reserved address space for future input-output devices. It is into this area that the XTIDE card maps the ROM BIOS located on the XTIDE Compact Flash card. The ROM address switch block allows you to select where in this area it maps to, starting from address C800. In order to address memory locations, the 8088 CPU uses an address bus. So whenever it needs to read or write to any memory location within the 1 MB address space, it puts the address of that memory location on the address bus and uses memory read or memory write control lines to signal that it wants to read or write data in that memory location. All I/O devices are also given an address as well. In our case, the XTIDE Compact Flash card has a switch block that sets the address to 300. In order to talk to the Compact Flash card adapter, the 8088 CPU has to put address 300 on the address bus. But hang on, isn't there also a memory location in the working memory with the same address? How does the CPU know it wants to talk to the working memory location 300 or an I/O device at location 300? Well, this is where the 8088 CPU uses different control lines and different internal instructions for either memory or input-output device access. In order to access memory, it uses the control lines memory read or memory write, as mentioned before. When it wants to access an I/O device, it uses different control lines called I/O read and I/O write. This helped me understand that the XTIDE compact flash adapter is actually two devices on the same PCB. On one hand, it's attaching the ROM chip containing the XTIDE firmware to the ISA bus. On the other, it's attaching the compact flash card to the same ISA bus. This understanding of mine simplified the diagnostic approach. If the XTIDE banner doesn't appear or has a wrong ROM address, the problem will lie in the connections between the ISA bus and the ROM BIOS chip. If you do get the XTIDE header information but no compact flash card found, the issue could lie in the I/O address or the path between the ISA bus and the compact flash card. One thing to note about the I/O address. The diff switch for the I/O address controls the address selection logic on the PCB. It has to match what the ROM BIOS chip has been configured for. By default, the ROM BIOS firmware is configured for I/O address 300. If you change the I/O address via the switch to something else than address 300, you have to reconfigure the XTIDE BIOS and either burn a new ROM BIOS chip with those changes, or if you can update the existing ROM BIOS chip, if that is possible on the board. As you probably seen in the photos, the ROM BIOS chip on my XTIDE card is an erasable EEPROM chip, and there's a switch setting on the switch block with the 8 diff switches that enables the ability to write or update this ROM BIOS chip. To do that, you need the XTIDE bin file, which is the new ROM firmware, plus the XTIDE configuration executable. You have to do this in DOS. It doesn't work in Windows. I decided not to update the firmware in this EEPROM because I knew it was working, at least on occasions, and therefore I wanted to make sure I could fall back to it if I needed to. So I programmed another EEPROM for the purpose of updating the firmware. But with that learning, I went onwards and decided to create a bit of a chart mapping all the pins of the ROM to the edge of the PCB so I could bus out the connectivity, and I'll show you how. So here's my handy cheat sheet for the connectivity between the ISA slot connectors and the BIOS ROM. Now I'm not showing you the multimeter, but I'm sure you can hear it. So what I do, I simply bus the connectivity or check the connectivity between the ISA slot connector and the ROM chip. So I've got D0 here on A9, and D0 should be, according to this, pin 11. So pin 11 is here. Then D1 is pin 12. And D2 is pin 13. This is D3, or data line 3, which is pin 15 on the other side. And so on. That way I can validate the connectivity between the ISA slot and the ROM chip. As I mentioned, some of the pins, or few of the pins, do not actually go to the ISO slot connector. Like pin 1 goes to a terminator, the terminating resistance. So you can easily check pin 1, and it goes here to pin 2 on the terminating resistor. And that is fine. So I could then verify the connectivity from the ISO slot and wherever else the pins on the socketed ROM go to. And doing it directly on the pin eliminates poor connectivity in the socket plus bad soldering. And that is how I found that one of the pins of the ROM didn't make a connectivity to the ISO slot. It was one of the address bus lines. So, my mistake, but that was easily fixed. So that's a good way of validating the connectivity to the ROM. So, I fixed that, and what happened then? So, what happened next? I rectified my soldering mistake with the socket, put the XTIDE card back in the 5150, fired it up, and it worked with the old or the older BIOS ROM chip, which I had put in the socket. But I noticed some weird things. If I booted it up with an address setting of C800, it would show C800. If I changed the ROM address to D000, like I wanted to, it would show some funny address like E00. I was scratching my head over this. Then if I put the new EEPROM in with the later version from -0 degrees, it was still weirder. I can show you how crazy that was. Now, one of the things you may not know is that when the IBM PC boots up, it scans the ROM area as part of its booting process, checks for any BIOS ROMs, and checks the checksum. If it finds an error in a checksum of a BIOS ROM, it actually gives an error message highlighting the ROM address of the failing ROM. So pumping out all these ROM addresses on the new EEPROM was just weird. I put the old one in, and yes, the old one seemed to work, but once again, the ROM address was EE00. Bit crazy. After scratching my head, I looked at the schematic, and I thought, maybe there's something wrong with the address selection switch, so let's have a look at that. Here is the XTIDE Compact Flash card as it came with its default settings, and I've sort of highlighted what the settings are. As you can see, it's set for IO address X300 or hex 300. The ROM is enabled, the EEPROM write is off, and then ROM address selection. And as you can see, it's set for on on, off, on, and number 8 isn't used. That's the ROM address selection switches. They say 11011, which should be the standard C800. Now, I'll put it in the PC and show you, but before I do that, I'll bust through the switches and you will see what's happening here. So I've just flipped it over like this, so the switch position should be the same. So if I bust through, you will hear it. You don't have to see the multimeter. But when I bust it through, here is the diff switch 1, on, and off, which isn't used. That works. And next we have diff switch 2, so 1, which should be on, 2, which should be off, then 3, which should be on, 4, which should be on, but 4 is not on. And then you have 5, which should be off. You have 6, which should be on, and 7, which should be on, and 8, which should be off. So the switch is broken, it's not making contact. So a simple way to test that is simply put all of them on. We'll bust through it again. I'll do that one as well, doesn't really matter, the first one. And then we can bust through all of them and they should all be on, 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 on. So switch 1 is okay. Switch 2 should be on. Now it's not on. Switch 2 should be on, and it is on. Let me go back to 1. Yeah, 1 is not connected. 3 should be on. Yeah, 4 should be on. 5 should be on. 6 should be on. 7, not entirely happy. Yeah, and 8, 7, 6, 5, 4. No, 3 is not working. 2, and now 1 is not working. So it's random, sometimes the same one, sometimes different ones. So that diff switch has to come out. Well, as you saw, I had to replace the address selection switch, and I changed both the 4 wide and the 8 wide switches with new ones because I simply didn't trust them. Once I put the new switches in, guess what? The card worked fine with the old ROM. It didn't work with the new ROM. And despite me having changed the switch, it was still showing EE00. And on the new ROM, it was still pumping out the errors for all the ROM addresses. This was a bit crazy. So I took the card and had a good look at it. I was trying to figure out what was happening, but it was obviously something in the address selection for the ROM. I was beginning to suspect that the U2 chip on the PCB was faulty. So I had a good look at it, and to my horror, and I should have gone through this before, well, it's never too late to learn, but one of the pins was unsoldered. And guess what? That's the plus 5 volts for the chip. I was scratching my head. Well, how did I miss that? We're now up to a number of problems. First, the R5 being soldered into a board. That wasn't my fault. The second one was the socket replacement, where I made a poor soldering of one of the address bus lines for the socket. That was my fault. The third one now is the switch. The switch had gone faulty randomly, which was just pretty crap. And then the fourth, not soldering the address selection chip for the ROM, or one of the legs. That wasn't my fault. And there is a fourth fault as well. Once I soldered the 5 volt pin on U2 and I put the card in, guess what? The address was correct. I finally got my D000. So I put the new EEPROM in, and it gave me this error. I couldn't believe it. It was an improvement. It was only D000 error. With that, I suspected there was something wrong with that EEPROM, despite me having put it back into the EEPROM programmer and verified the contents. So I burnt a second one, put it in. It now works perfectly. I'm finally with a XTIDE Compact Flash Card Lite that works and is not giving me any grief. Wow! It's working with the new BIOS. Fantastic. Well, diagnosing and getting this XTIDE Compact Flash Card working has taken far longer than I expected. Anyway, it's finished now and it's working, so I'm happy with that. Some of the key learnings from this is to firstly not trust somebody else's soldering skill. If you buy a pre-made PCB with components soldered on it, just double check that all the components are properly soldered. Secondly, double check your own work if you do some soldering, which I should have done but ended up doing. And thirdly, if you have a problem with something, you need to understand how it works or seek some help on forums where people can guide you in the right direction. Now, I did create this continuity testing pin-out chart for the Compact Flash card 4.1 Lite. So if you have the same card and have some issues, I'll put a link to that PDF file down below. I also did create a chart for the Compact Flash card, given that there are two separate pathways on the PCB, one to the ROM and the other to the compact flash card. So you can bus through from the edge of the card to the compact flash card as well. But anyway, thanks very much for stopping at the eCave today. Until next time, goodbye.